Hello everyone, I'm Yazan Ibrahim, or as some of you might know me, Yazan Abu Ghosh. Today we're going to dive into a fascinating and essential topic. Welcome back. Having set the stage for AI operations in our introduction to part 2, we're now ready to roll up our sleeves and get into the nitty-gritty. Our focus today is on something that is absolutely fundamental to everything that follows in the AI journey. Chapter 6, Data Management Specific to AI. It cannot be overstated. Effective data management is the bedrock upon which successful, reliable, and ethical AI systems are built. AI models, at their very core, are data-driven entities. The quality, the characteristics, the lineage, and the governance of the data used for training, testing, and ongoing operation directly and profoundly impact their performance, their fairness, their security, and their overall trustworthiness. Get the data wrong or manage it poorly, and even the most sophisticated algorithm will falter. Throughout this chapter, you'll notice that the principles and practices we discuss are not arbitrary. We must focus our research and understanding on established guidance. Much of what we'll cover is deeply informed by and aligns with leading frameworks such as the NIST AI Risk Management Framework, AI RMF, a whole suite of ISO IEC standards, including ISO IEC 42001 on AI management systems, ISO IEC 23894 on AI risk management, and ISO IEC TR 24028 concerning trustworthiness in AI, among others. Furthermore, insights from professional bodies like ISACA and the AAIA Institute of Internal Auditors, along with a wealth of other academic and industry research, all point towards the critical importance of robust data management in the AI context. So let's dive in. Let's begin at the very beginning of the data journey for AI. Section 6.1, Data Collection. Data collection is the initial and arguably one of the most critical phases in the entire AI lifecycle. It involves the systematic process of gathering raw data from a multitude of various sources. And it's crucial to state up front, ethical data collection is an absolute prerequisite for building ethical AI. If ethics are compromised at this stage, it taints everything that follows. Why is data collection so important? Firstly, it provides the foundation for learning. AI models, especially machine learning models, learn patterns and relationships from the data they are fed. Without data, there is no learning. Secondly, the characteristics of the collected data directly impact model performance. Biased, noisy, or irrelevant data will lead to poorly performing models. Thirdly, this is often the primary point of bias introduction. If the data collected doesn't accurately represent the real world or the population the AI will affect, biases can creep in and become embedded in the model. And finally, data collection is heavily governed by ethical and legal compliance requirements. Organizations must adhere to privacy laws, ensure consent where needed, and be transparent about data usage. So what are the key considerations and best practices for data collection in an AI context, keeping in mind the rigorous standards expected by frameworks like ISO IEC 42001 and the principles of trustworthy AI? Define clear objectives and data requirements. Before collecting any data, you must have a crystal clear understanding of what the AI system is intended to do and what specific types and attributes of data are needed to achieve that objective. This clarity prevents collecting unnecessary data, a principle underscored by many data governance frameworks. Identify diverse and reliable sources. Seek out data sources that are not only rich in information but also reliable and crucially diverse. A lack of diversity in data sources is a common pathway to biased AI models. Consider internal databases, public datasets, third-party providers, sensor data, and more. Ensure ethical and legal compliance. This is non-negotiable. Adhere strictly to privacy regulations like GDPR, CCPA. Obtain informed consent when collecting personal data. Implement anonymization or pseudonymization techniques where appropriate. Clarify data usage rights, especially when using third-party data. And maintain transparency with data subjects about how their data is being collected and used. Ethical guidelines from bodies like ISACA and principles within the NIST AI RMF strongly emphasize this. Focus on data quality and relevance. It's not just about quantity. The quality and relevance of the data are paramount. Ensure the data is accurate, current, and directly pertinent to the problem the AI aims to solve. Address potential bias from the outset. Proactively think about and address potential sources of bias during data collection. Strive for representative data that accurately reflects the diversity of the population or context the AI will operate in. This often involves targeted efforts to collect data from underrepresented groups. Consider data volume and sufficiency. While quality is key, AI models, especially deep learning models, often require a significant volume of data to learn effectively. Assess whether you have or can collect enough data for the task at hand. Choose appropriate collection methods and tools. Select methods, e.g., surveys, APIs, web scraping, IoT sensors, and tools that are suitable for the data sources, ensuring they are secure and efficient. Thorough documentation and metadata. This is critical for traceability and governance, a point heavily stressed in standards like ISO or IEC 42001. Document everything: the provenance of the data, where it came from, the collection methodologies used, any known limitations or biases in the data, and records of consent. Rich metadata is invaluable. Secure storage and transmission. Ensure that data is stored and transmitted securely from the point of collection to prevent breaches or unauthorized access, aligning with security best practices. Adopt an iterative approach. Data collection is often not a one-time task. You might need to revisit and refine your collection strategies as you learn more about the data and the AI model's performance. Despite these best practices, data collection faces several challenges. Data availability: the required data may simply not exist or be accessible. Cost and effort: collecting, labeling, and validating high-quality data can be extremely time-consuming and expensive, ensuring representativeness. Achieving a truly representative data set that avoids all forms of bias can be very difficult. Dynamic environments. In rapidly changing environments, data collected in the past may quickly become outdated or irrelevant. Ethical dilemmas. Situations may arise where the need for data conflicts with ethical principles or individual rights, requiring careful navigation. Once data is collected, we need to organize it. This brings us to section 6.2, data classification. Data classification in the context of AI is the process of organizing data into categories based on its type, sensitivity, value, and relevance to the AI application and the organization. This systematic categorization is what enables granular security controls, appropriate privacy measures, and effective access management, all of which are fundamental to responsible AI. The importance of data classification for AI cannot be understated. It directly enables effective security and access control. By knowing the sensitivity of data, you can apply proportionate security measures. It's crucial for compliance with data protection and privacy regulations, which often mandate different handling procedures for different types of data. It aids in risk management by helping to identify high-risk data that requires more stringent protection. It contributes to data quality and relevance by ensuring that AI models are trained and operate on appropriately categorized and relevant data. It's a cornerstone of privacy protection, particularly for personal or sensitive information. It leads to efficient data management, as different categories of data may have different storage, retention, and disposal requirements. It can even assist in bias detection, as classifying data by demographic attributes can help in analyzing representation. Ultimately, it supports informed model development by providing clarity on the nature of the data being used. What are the key considerations and steps in implementing data classification for AI, reflecting best practices promoted by governance frameworks? Define classification levels and criteria. Establish clear, objective criteria and a defined set of classification levels, e.g. the public, internal, confidential, highly confidential. These criteria should consider factors like sensitivity, regulatory impact, and business value. Identify data subject to AI. Scope out all the datasets that will be used for developing, training, testing, and operating AI systems. Understand data attributes and context. Analyze the specific attributes within each dataset and understand the context in which the data was created and will be used by the AI. Involve data owners and stewards. Data owners and stewards have the best understanding of their data and should be central to the classification process. This aligns with the accountability principles in data governance. Use a combination of automated and manual methods. Automated tools can help with initial classification, especially for large volumes of data, but manual review and validation by experts are often necessary, particularly for sensitive or complex data. Tag and label data. Once classified, data should be appropriately tagged or labeled with its classification level, both in its metadata and potentially within the data stores themselves. Develop handling policies based on classification. Create clear policies and procedures for how data at each classification level should be handled, accessed, stored, transmitted, and disposed of. Integrate with AI governance and security frameworks. Data classification should be an integral part of the overall AI governance and information security frameworks, not a standalone activity. This is a key tenet of holistic systems like an AIMS based on ISO IEC 42001 regular review and reclassification. Training and awareness ensure that all personnel who handle data are trained on the data classification scheme and their responsibilities. As needed. What types of data classification are relevant to AI? Sensitivity-based classification. This is common, categorizing data as, for example, public, internal use only, confidential or restricted, highly confidential, content-based classification. Categorizing data based on what it contains, such as personally identifiable information, PII, financial data, health information, intellectual property, etc. Compliance-based classification. Classifying data based on specific regulatory requirements, such as GDPR subject data, HIPAA data, PCI DSS data, etc. AI-specific classification. It's also useful to classify data based on its role in the AI lifecycle, such as training data, validation data, and test data, as these may have different handling and quality requirements. Data classification also comes with its challenges. Volume and variety of data. The sheer scale and diversity of data used in AI can make classification a daunting task. Dynamic data. Data that is constantly changing or being updated can be difficult to classify consistently. Inferred sensitivity. AI models can sometimes infer sensitive information from seemingly non-sensitive data, making it hard to classify the original data accurately for all potential risks. Balancing utility with protection. Overly strict classification might hinder data accessibility and utility for AI development, while too lenient classification can increase risks. Finding the right balance is key. Closely linked to data classification is Section 6.3, Data Confidentiality. Data confidentiality in the context of AI refers to the critical task of protecting data from unauthorized access, disclosure, or use throughout its life cycle. AI introduces new and complex vectors for potential confidentiality breaches, such as sophisticated attacks like model inversion, which tries to reconstruct training data from the model itself. The importance of data confidentiality in AI is multifaceted. It's fundamental for protecting sensitive information, including personal data, trade secrets, and other proprietary business information. It's essential for compliance with data protection laws like GDPR and industry regulations. It builds and maintains trust with customers, partners, and the public. If people don't trust you to keep their data confidential, they won't engage with your AI systems. It prevents misuse of data for unauthorized or malicious purposes. It plays a role in safeguarding intellectual property IP, especially the AI models themselves, which are valuable assets trained on potentially confidential data. It is a cornerstone of ethical AI, respecting individuals' rights to privacy. So, what are the key considerations and measures for ensuring data confidentiality in AI systems, reflecting guidance from security standards and frameworks like NIST? Data classification. As we just discussed, this is the foundational step. You can't protect data effectively if you don't know its sensitivity level. Strong access controls. Implement robust access control mechanisms. This includes role-based access control, RBAC, and attribute-based access control, ABAC, to ensure users only access data relevant to their roles and attributes.
Encryption. This is crucial. Encrypt data in transit as it moves across networks and at rest while it's stored.
Consider encryption for AI models themselves as well. Anonymization and pseudonymization, techniques to de-identify data. However, always be aware of re-identification risks, as AI techniques can sometimes undermine these measures. Privacy-enhancing technologies, PTs. Explore and implement PTs where appropriate. We touched on these before, things like federated learning, training models on decentralized data without moving raw data, and differential privacy, adding statistical noise to protect individual records. Secure data storage and environments. Ensure that data, especially sensitive training data and models, is stored in secure environments with hardened infrastructure and appropriate physical and logical security controls. Data masking and obfuscation for non-production environments like development or testing. Use data masking or obfuscation techniques to hide real sensitive data while still providing realistic data for development purposes. Secure data disposal. Implement processes for securely deleting or destroying data when it is no longer needed, in line with retention policies and regulatory requirements. Regular security audits and penetration testing. Conduct periodic audits and penetration tests to identify and remediate vulnerabilities in systems that handle AI data. Employee training and awareness. Educate employees about data confidentiality policies, procedures, and their responsibilities in protecting data. Non-disclosure agreements, NDAs. Use NDAs with employees, contractors, and third parties who may have access to confidential AI data or models. Robust incident response plan. Have a well-defined plan in place to respond to and mitigate the impact of any data confidentiality breaches.
Comprehensive monitoring and logging. Continuously monitor systems for suspicious activity and maintain detailed logs to aid in detecting and investigating potential breaches. There are also specific confidentiality challenges in AI that require special attention. Model inversion attacks. As mentioned, attackers attempt to reconstruct sensitive training data by repeatedly querying the AI model. Membership inference attacks. Attackers try to determine whether a specific individual's data was part of the model's training set. Confidentiality of the AI models themselves. The models representing significant IP can be targets for theft or unauthorized copying. Explainability. Data revealing inputs. Sometimes the data used to explain an AI model's decision might inadvertently reveal sensitive input data. Federated learning nuances. While pets like federated learning enhance privacy, they are not a silver bullet and have their own potential vulnerabilities that need to be understood and managed. Now let's shift our focus to a characteristic that is perhaps the most talked about aspect of data in AI. Section 6.4, Data Quality. Data quality in the context of AI refers to the fitness of data for its intended purpose in training, testing, and operating AI systems. It's not an absolute measure, but rather a multifaceted concept that is highly contextual to the specific AI application and its objectives. The old adage, garbage in, garbage out, Gigo, is more relevant than ever in the world of AI. The importance of data quality for AI cannot be overstated. It directly and profoundly impacts model performance. High-quality data leads to more accurate, reliable, and robust AI models. Poor quality data inevitably leads to poor performance. It is crucial for bias mitigation. Biases often stem from poor quality or unrepresentative data. Ensuring data quality is a key step in building fairer AI systems. It underpins trustworthiness. AI systems built on high-quality data are more likely to be trusted by users and stakeholders. This aligns with the trustworthiness characteristics outlined in ISO/IEC TR 24028. It's essential for compliance. Many regulations require data accuracy and integrity, especially when AI makes decisions affecting individuals. It leads to more efficient development. Working with clean, well-structured data can significantly speed up the AI development process. It contributes to robustness. High-quality data helps create models that are more resilient to noise and variations in real-world inputs. It reduces operational risks associated with AI systems making incorrect or unreliable decisions due to faulty data. What are the key dimensions of data quality that we need to consider? There are many, and standards like ISO/IEC 42001 emphasize documenting these characteristics for data used in AI systems. Accuracy. Does the data correctly reflect the real-world facts or events it represents? Completeness. Is all the necessary data present? Are there missing values or records? Consistency or uniformity. Is the data consistent within itself and across different data sets? Are there contradictions? Timeliness or currency. Is the data up to date and relevant for the time period it's being used for? Stale data can lead to poor predictions. Validity or conformity. Does the data conform to defined business rules, standards, or formats? Uniqueness or non-duplication. Are there duplicate records that could skew analysis or model training? Relevance. Is the data appropriate and pertinent to the specific AI task at hand? Representativeness. Does the data accurately reflect the diversity and characteristics of the population or phenomenon it's intended to model? This is key for avoiding bias. Integrity. This refers to the structural soundness of the data and its relationships, often maintained through database constraints. Provenance or lineage. Knowing the origin and history of the data, including any transformations it has undergone. This is vital for traceability and understanding potential quality issues. What processes and best practices can help ensure high data quality for AI? Many of these are echoed in the guidance from ISACA on data management and IT governance. Establish data quality standards and policies, clearly define what data quality means for your organization and specific AI applications, and establish policies to enforce these standards. Data profiling and assessment. Systematically analyze data sets to understand their characteristics, identify quality issues, and assess their fitness for use. Data cleaning and pre-processing. Implement processes to correct errors, handle missing values, remove duplicates, standardize formats, and transform data into a usable state for AI models. Data validation. Implement checks and validation rules at various stages of the data lifecycle to ensure data meets predefined quality criteria. Version control for datasets. Just like code, datasets used for AI should be versioned so that experiments are reproducible and changes can be tracked. Documentation of data quality processes. Thoroughly document all data quality assessment and improvement processes for transparency and auditability. AI is addressed in section 6.5, data balancing. Data balancing techniques are used to address the problem of imbalanced datasets. This is where different classes or categories within the data are not equally represented. For example, in a fraud detection dataset, legitimate transactions might vastly outnumber fraudulent ones. If not addressed, such imbalances can heavily bias AI models towards the majority class, leading them to perform poorly on or even ignore the minority class. Data balancing is a key intervention for achieving more ethical and equitable AI outcomes. The importance of data balancing is clear. It leads to improved minority class performance. Models trained on balanced data are generally better at predicting and identifying instances of the less frequent class. It's a crucial tool for bias mitigation. Imbalanced data is a major source of bias. Balancing helps to create fairer models. It can lead to enhanced robustness of the AI model, making it more stable when encountering real-world data that might also have varying class distributions. It allows for more accurate evaluation of model performance. Standard accuracy metrics can be misleading on imbalanced datasets. Balancing can help provide a clearer picture when used with appropriate evaluation metrics. It helps in meeting ethical and regulatory requirements that mandate fairness and non-discrimination. It helps in avoiding overlooking critical events, especially when the minority class represents something important, e.g., a rare disease, a critical system failure, fraudulent activity. There are several common techniques for data balancing, generally falling into two categories. First, data-level approaches, which modify the dataset itself. Oversampling, increasing the number of instances in the minority class. Random oversampling, simply duplicating random instances from the minority class. SMOTE, synthetic minority oversampling technique. A popular technique that creates synthetic samples for the minority class by interpolating between existing minority instances. ADASIN, adaptive synthetic sampling. Similar to SMOTE, but focuses on generating more synthetic data for minority class samples that are harder to learn. Undersampling, decreasing the number of instances in the majority class. Random undersampling, simply removing random instances from the majority class. Tomic links, identifying pairs of instances from different classes that are close to each other, tomic links, and removing the majority class instance from such pairs. Near miss, selects majority class samples whose average distance to some minority class samples is smallest. ENN, edited nearest neighbors, removes any instance whose class label differs from the class of the majority of its k-nearest neighbors, hybrid approaches, combining oversampling and undersampling techniques such as SMOTE ENN or SMOTE TOMEC. Second, algorithm-level approaches, also known as cost-sensitive learning, which modify the learning algorithm rather than the data. Cost-sensitive classification, assigning a higher misclassification cost to the minority class. This forces the model to pay more attention to correctly classifying minority instances. Modifying the decision threshold, adjusting the classification threshold of the model to be more sensitive to the minority class. When dealing with data balancing, there are several considerations and best practices. Understand the cause of imbalance. Is it natural or due to data collection issues? Choose the right technique. There's no one-size-fits-all solution. The best technique depends on the dataset, the model, and the problem. Experimentation is often needed. Apply balancing correctly in cross-validation. Crucially, balancing techniques, especially oversampling, should generally be applied only to the training set within each fold of cross-validation, not to the validation or test sets, to avoid data leakage and get a realistic performance estimate. Evaluate with appropriate metrics. Standard accuracy can be misleading. Use metrics like precision, recall, F1 score, area under the ROC curve, AUC, or precision, recall, AUC, especially for the minority class. Be mindful of overfitting and underfitting. Oversampling can sometimes lead to overfitting on the minority class, while undersampling can lead to losing important information from the majority class. Consider the cost of misclassification. If the cost of misclassifying minority instances is very high, this should influence your choice of technique and evaluation. Leverage domain knowledge. Understanding the problem domain can provide insights into which balancing techniques might be most appropriate. Start simple. Sometimes simpler techniques work well. Consider not balancing if the model is robust. Some algorithms are inherently more robust to class imbalance, or the imbalance might accurately reflect the real-world problem where identifying the majority class correctly is the primary goal. What happens when you don't have enough data to begin with? This brings us to Section 6.6, Data Scarcity. Data scarcity refers to situations where there is an insufficient volume or variety of data available for effective AI model training, validation, or operation. While we often hear about big data, many practical AI projects, especially in new or niche domains, grapple with the challenge of limited data. Addressing data scarcity often requires creative solutions and a shift in approach. The importance of addressing data scarcity is clear because it directly impacts model performance, often leading to underfitting, where the model fails to learn the underlying patterns in the data, reduces the generalizability of the model to new unseen data, can lead to bias amplification, as the model might overlearn from the few examples it has, especially if those examples are not fully representative. Makes it difficult to handle minority classes effectively, as there might be very few examples of them. Hinders innovation, as lack of data can be a major bottleneck for developing new AI applications, increases development time and cost, as more effort might be needed to extract value from limited data or to acquire more. Can lead to overfitting, where the model learns the training data too well, including its noise, and performs poorly on new data. Common scenarios where data scarcity is encountered include new domains or problems, where historical data simply doesn't exist. Rare events. For tasks like detecting rare diseases or predicting infrequent but critical failures, by definition, there will be few examples. Privacy concerns, where legal or ethical restrictions limit access to or use of available data. High cost of data acquisition or labeling. In some fields, obtaining or accurately labeling data can be prohibitively expensive or require specialized expertise. Cold start problem. When launching a new product or service, there's often no initial user data to train personalization models. Niche applications. AI for highly specialized tasks may have a very limited pool of relevant data. Fortunately, there are several techniques to mitigate data scarcity. Data augmentation, creating new synthetic data points by applying various transformations to existing data. For images, this could be rotating, flipping, or changing brightness. For text, it could involve paraphrasing or synonym replacement. Transfer learning. This is a very powerful technique. It involves leveraging knowledge from a pre-trained model, often trained on a very large dataset like ImageNet or large text corpora, and adapting it to a new related task where data is scarce. Few-shot, one-shot, and zero-shot learning. These are advanced machine learning approaches designed to enable models to learn from very few, just one or even no labeled examples of a particular class, often by leveraging knowledge about other classes or auxiliary information. Synthetic data generation, using techniques like generative adversarial networks, GANs, or variational autoencoders, VAEs, to create entirely new artificial data samples that resemble the original data distribution. This is increasingly being explored, and research from bodies like NIST often touches on the validation of such synthetic data. Active learning, an approach where the model itself can query a human, an oracle, for labels on the most informative unlabeled data points, making the labeling process more efficient when resources are limited. Semi-supervised learning, using a combination of a small amount of labeled data and a larger amount of unlabeled data to train a model. Simplify the model. Using simpler models with fewer parameters can sometimes perform better when data is scarce, as complex models are more prone to overfitting. Feature engineering and selection. Carefully crafting relevant features from the available data or selecting only the most informative features can help models learn more effectively from limited data. Regularization techniques. Applying techniques like L1 or L2 regularization or dropout to prevent models from becoming too complex and overfitting the scarce training data. Ensemble methods. Combining predictions from multiple models and ensemble can sometimes lead to better performance and generalization, even with limited data. Data sharing and collaboration. Exploring opportunities to securely and ethically share or pool data with other organizations, or participate in data collaboratives. while respecting privacy and competition laws. Strategic considerations are also vital. Realistic scoping. Be realistic about what can be achieved with limited data. Investing in data acquisition. If data is crucial, strategically invest in acquiring or creating more high-quality data over time. Focus on quality over quantity. When data is scarce, the quality of each data point becomes even more critical. Iterative development. Start with what you have, build an initial model, and iteratively improve it as more data becomes available or as you refine your techniques. Finally, let's address section 6.7, data security in the context of AI. Data security for AI involves protecting all AI-related data, including training data, validation data, test data, and data processed by live AI systems throughout its entire life cycle. Crucially, it also extends to securing the AI models themselves, which are valuable intellectual property and can be targets of attack. A modern approach integrates security throughout the AI lifecycle, often referred to as DevSecOps for AI or MLOps security. This proactive stance is vital, as emphasized by comprehensive risk management frameworks. The importance of data security in AI is paramount. It's about protecting sensitive information from unauthorized access, theft, or disclosure. It aims at preventing unauthorized access to data and AI systems. It's key to maintaining the integrity of data, ensuring it's not tampered with or corrupted, as this could lead to flawed AI decisions. It ensures compliance with data protection regulations and industry-specific security standards. It involves safeguarding the AI models themselves, which represent significant investment and intellectual property. It builds and maintains trust with users and stakeholders. Security breaches erode trust very quickly. It's critical for mitigating AI-specific threats such as data poisoning attacks, corrupting training data, model stealing, or adversarial attacks designed to fool AI systems. It helps in preventing disruption of AI-driven services due to security incidents. It is fundamental for ethical deployment, as secure systems are a prerequisite for responsible AI. What are the key considerations and measures for ensuring robust data security in AI, often following a defense-in-depth strategy? Guidance from NIST's Cybersecurity Comprehensive Security Risk Assessment. Specifically, identify and assess the security risks related to AI data, models, and infrastructure. Strong authentication and authorization. Implement robust mechanisms like multi-factor authentication, MFA, role-based access control, RBAC, attribute-based access control, ABACI, and the principle of least privilege encryption. Encrypt data at rest, in transit, and consider encrypting the AI models themselves. Secure data storage and infrastructure hardening. This includes securing MLOps environments, databases, and any cloud services used for AI. Data loss prevention. DLP. Implement DLP tools and policies to prevent sensitive AI-related data from leaving secure environments. Network security. Utilize firewalls, intrusion detection, prevention systems, IDS/IPS, and network segmentation to protect AI systems and data. Secure Software Development Lifecycle, SSDLC for AI. Embed security into every phase of AI system development. This includes security by design principles, static application security testing, SAST, and dynamic application security testing, DST, protection against AI-specific attacks. Implement defenses against attacks like input validation and sanitization to prevent injection attacks, and techniques like adversarial training to make models more robust against attempts to fool them. Data minimization and de-identification. Only collect and retain necessary data and use anonymization or pseudonymization where feasible to reduce the impact of potential breaches. Regular security audits, vulnerability assessments, and penetration testing proactively identify and remediate security weaknesses. Comprehensive incident response plan. Have a well-tested plan to respond effectively to security incidents involving AI systems or data. Employee training and security awareness. Educate all personnel on AI security risks and best practices. Third-party and supply chain security management. Assess and manage the security risks associated with any third-party vendors or components used in AI systems. Robust monitoring, logging, and alerting. Implement comprehensive security monitoring using tools like security information and event management, CM systems, to detect and respond to threats promptly. The classic CIA triad, confidentiality, integrity, availability, remains foundational in AI data security. Confidentiality, ensuring data is accessible only to authorized individuals. Integrity, ensuring data and models are accurate, complete, and have not been improperly modified. Availability, ensuring that AI systems and their data are accessible and usable when needed by authorized users. Finally, the role of governance is critical for data security in AI. This involves establishing clear security policies and standards specific to AI. It requires defined roles and responsibilities for AI data security, and it necessitates regular review and updating of security measures to keep pace with evolving threats and technologies, a principle central to frameworks like ISO IEC 42001. Effectively managing data for AI from collection through security is a complex but absolutely vital endeavor. It requires a holistic approach grounded in established principles and practices to build AI systems that are not only powerful but also trustworthy and responsible. Thank you for watching, and as always, continue learning, stay curious, and we'll see you next video.